Yeah, thanks, Niels. And apart from the organizers and everyone who made this possible, I also want to thank Chi-Tian, who agreed to swap his talk slot with me. Okay, so the motivation for me, the motivation for this project is there are many type theories that people in our community have proposed, and how can I understand them? And I mean, in particular, there are many times that people propose type theories to solve a specific problem, and someone else suggests another type theory to also address this problem. So how can I know how these two theories compare? So many times, let me see right. So many times the way that a new type theory gets proposed is like this. Like we start from some type theory, T1, that we already know, and where we already know how it behaves. And then, well, people say, okay, if we could extend it a little bit to, well, have some additional properties or some additional abilities, then it would be more suitable for whatever we actually want to do. So when I started doing type theory, people liked normal Martin-Löf type theory a lot. But people also often just said, well, actually, we also would like function extensionality, so let's just add it as an axiom. And that's very easy to understand for me because you can still use the same proof assistant. Like, let's say, first you use, sorry, I want to go back. First you use ACTA for MLTT, and then you postulate funnext to get some slightly new variation where you can do a few new things. And then after some time, people started postulating univalence instead, which I think probably should be called universe extensionality. But now that it's called univalence, I'm also happy enough with that. And I mean, it's very easy to compare these two extensions, right? Because we can prove internally to MLTT that univalence will imply function extensionality. So if someone does something in ACTA where function extensionality is postulated, then we can also do this in ACTA where univalence is postulated. Okay, but so these are axiomatic, well, I call them axiomatic extensions. So they are easy to understand. Now there's a second kind of extension, which I think, for me at least, is much harder to understand. Where again, you start with homotopy type theory or some other type theory, and then you just change the structure to get, for example, simplicial type theory or directed type theory, or, I mean, there are many different versions of directed type theory, and all of them work slightly differently, but they are expected to do similar things. And right, so how am I able to compare how they correspond to each other? And so since I find axiomatic extensions easier than structural extensions, my approach here is that I want to take a structured extension like T1 to T2, and I want to present it as an axiomatic extension. And the way that we want to do this is to say, well, let's go from T1 to some two-level type theory over T1. So this itself is already a structured extension because essentially we are adding more structure, but in some sense this is relatively harmless structure because as long as we don't make additional assumptions, this extension is conservative. So everything we can do in here about the original T1 is the same stuff that we could already have done in here. So we haven't actually changed anything. So I will say a bit more about what I mean by two-level type theory. I think some people in previous talks have already talked about this. But okay, and so I mean, in a nutshell, two-level type theory just gives us some additional language to talk about a type theory. So it's like you take a type theory and then you just add some of the meta theory of this type theory and allow yourself to talk about this meta theory. So it's well, the motivating construction is to start with a type theory T, maybe represented by some category, and then you take presheaves on this category. So now the original category that you have still lives in this category of presheaves over it in the form of representables, but you also have more presheaves lying around that you can use to talk about. Okay. And then, so if everything goes well, in this richer language, we can now formulate some axioms which mirror this original structural extension here. Okay. Right. So two-level type theory originally was well, it originally goes back to Wygotsky, who suggested a system that he called homotopy type system. I'm still not sure why he chose that name. I'm not sure whether it's a very good name, but anyway, he called it HTS. And it was motivated by his simplistic set model. So if you look at the simplistic set model of Wygotsky, there is this model of homotopy type theory sitting inside, but you can also consider a bigger model of extensional type theory given by simplistic sets. So the connection is that if you take simplistic sets and you say that, well, your contexts are simplistic sets, then you can either say that only the Kant vibrations over a given context are types, then you get Wygotsky's simplistic set model, or you say, well, all vibrations could be types, then you get something that is closer to, well, some Hoffman-style model of extensional type theory. Okay, so a two-level type theory, well, anyway, a two-level type theory so consists of, well, two type theories which share a category of context. So the left part here is the type theory that we are actually interested in. So I present this in the form that Thorsten likes as a category with families of context, types, and terms. And so then there's a second level, which is also context, types, and terms, but maybe different types and terms, which forms this second layer or the outer layer. So these two type theories are connected by a conversion functor C. And the condition here is that this diagram commutes. So what does this mean? If we formulate this differently, we could formulate this as, well, two type theories here. And the condition that this here commutes has some consequences. Namely, it has the consequence that the two theories essentially share certain type formers, like pi and sigma and unit. One other way to view this is to say that, well, in many cases, the outer type theory is actually bigger, or, well, yeah, maybe let's say the outer theory is maybe bigger than the inner theory. So the outer theory could be extension Martin-Löf type theory, and somewhere inside sits homotopy type theory. No, so not all types of this extension Martin-Löf type theory are part of HOT, but some of them are, and those that are behave like, I mean, like if we ignore all the stuff outside, then this small fragment really behaves like a normal homotopy type theory. Okay, any questions so far? No. Yeah, please.
That version, yeah.
Sorry, this one? No, well, yes. Yes, actually, I think that is a pullback, yes. Okay. Right, so here's one example. So when I learned about Real and Schulman's simplicity type theory, well, Well, I mean, okay, some people here have already talked about Wheel and Schulman simplicial type theory. So essentially, this is homotopy type theory, and you have, well, in Wheel and Schulman's original formulation, they have, well, additional layers of contexts, which is why this is a structural extension. And these additional layers of contexts allow you to talk about shapes and shape inclusions. So you can, for example, talk about triangles and the inclusion of the boundary of a triangle into the triangle. And so these shapes then allow you to talk about extension types, like extending a type, extending a type that is fixed on a subshape to a type on the bigger shape. Okay, and for the last 5 minutes or so, I will just quickly sketch how this would work in this picture. So, I mean, this example is only partially worked out. So, in particular, what is not clear yet to me is whether this bottom extension here is still conservative. But I would expect it to be conservative in a reasonable sense, so that you can really say that this extension here that we are constructing really corresponds to the original real Schulman theory. Okay, so the first ingredient of simplicial homotopy type theory, as I mentioned, are extension types. So these are exactly these things which are nowadays probably most famous because they feature in cubical type theories. So the idea is that you have a shape and you have a subshape and you have a type which is defined on the whole shape, and you have a term of this type, but this term is only defined on the subshape. Like, say you have a term which is defined on triangles, and you already know you have a type which is defined on a triangle, and you already know that you want a term which, for the boundary of this triangle, has a certain form. And so then you want to consider the type of possibilities to extend this term to the whole shape. In two-level type theory, well, in simplicial type theory, this is really some hard-coded built-in thing. The same sort of thing exists naturally in two-level type theory, because there you can, I mean, if you can talk about types which are fibrant, which means they really come from the inner theory which we are interested in, like from what, then you can look at this picture and you can say that this map from L to K is a cofibration if, whenever you have such a square, this type of diagonal fillers here, which makes everything commute, is again fibrant. So again, can be considered as something which comes from the theory of interest, while all the rest outside, well, it comes from the auxiliary language, which is the outer theory. Okay, so now if you take a special case of this, where L and K are these shapes, is the shape inclusion, and the bottom map is just the identity, then you recover exactly this case of an extension type in the real Schulman sense. Right, so this is a fairly simple observation, but so if you work in two-level type theory, then extension types are not something that you have to assume to exist in the theory, but they are something that you can construct. Okay, and so the second ingredient which is needed for simplicial type theory are these simplicial shapes. So because so far, well, we have these extension types and we have this we have these shapes lying around, but we need some very specific shapes. And so in real and Schulman's setting, this is done by saying that, well, on the shape layer, context layer, we have a certain bounded total order or some variation of it. And then from this, we can encode all the simplicial shapes that we want. Like, for example, this bounded total order comes with an interval directly. So this interval already is one of the simplest simplicial shapes that we probably want. And then from this, we can build up some more complicated shapes. Like we can build up all the like k-dimensional triangles or also boundaries of k-dimensional triangles. So now in two-level type theory, we could either do exactly the same, or we could also just say on the outer layer, we could give ourselves all the shapes, or well, on the outer layer, we can actually define the category of shapes that we want. So this again is actually something that we can define, not postulate. And then we can postulate a certain functor from the outer level into the universe, no, from this category into the universe, which gives us exactly these shapes that we can then work with. Okay, right. So far, I've always said that the inner type theory of this two-level setting is homotopy type theory. This is pretty much fixed because this is really the theory that we are interested in and the theory that has infinity groupoids as primitive objects. So there's not very much we can choose here. But we haven't actually put many requirements on the outer theory. So I said that we can think of the outer theory as some sort of meta theory of Hot. But I mean, so far, everything we have done didn't really require us to make a choice. Yeah, so the first canonical choice is to say that the outer theory is extensional Martin-Löf type theory. So it really behaves like the meta theory of Hot. Another choice is to say that the outer theory is just homotopy type theory again, and the conversion functor between them is the identity. So then we get this picture. And so this leads to an approach which lives purely in homotopy type theory, and it's the same approach that Ulrich talked about, I think, 2 days ago. The other approach, where you say that the outer layer is extensional Martin-Löf type theory, is closer to the original suggestion of Real and Schulman, and it has the advantage that you have strict equalities that you don't need to treat as data, but they are really just properties. And there's the tiny advantage that it's slightly more general because you don't need to assume that all these shapes are vibrant or they are things in Hot. Yeah, so when I learned about this internal approach, I found it a bit puzzling that this also works, but in hindsight, it's actually not very surprising that this works. If we consider the projection map from sigma xy to x, and we consider some point in x, we can ask ourselves, well, what is the fiber over this point x0? And so one would say that the strict fiber is just y of x0. Well, that makes sense, but this is not what we get if we just take the usual definition of the homotopy fiber of an arbitrary function. If we apply that definition and just calculate what it is, then we will get something like this, like some other point in x and y of x, and an equality that x is equal to x0. But of course, then these two different fibers are equivalent. So we are happy, and I think this in a nutshell explains why these two theories lead to very similar things. Okay, thanks.